In this movie, we will discuss the value of bloodstain patterns and the information that you can learn by an examination of blood droplets and the patterns which they create. There's a good deal of misinformation in this area, and in particular, there are those who, with very little experience and or training, extrapolate beyond what they should. As I have mentioned before, the biggest problem with experts is not what they know, but what they testify to beyond what they know. And that happens quite often in the area of bloodstains. I just completed a case in which a police officer who had gone to a one-week school several years prior examined a pair of trousers on which there were some blood stains and determined from those that the owner of the pants had been standing next to a gunshot victim and therefore must have been the shooter. He said this blood speckles on his pants were high-speed gunshot residue or gunshot blowback patterns, and from that he stretched out his conclusions to accuse the defendant of being the shooter. I examined the pants, and they were in fact not bloodstains from blowback, but bloodstains from him assisting the victim up the stairs and getting blood brushed onto his pants from the bleeding victim. So the word to the wise is, don't attempt to extrapolate beyond what is your area of expertise, and basically don't make conclusions based on one or two blood spots, but on the entirety of the pattern. That being said, let's talk about what we can learn. First, I'm going to say that what we do with blood is not something that only blood does. Many of the basic experiments done to verify pattern analysis were done with milk. It's a matter of physics, and virtually any liquid will react the same way that blood does. Of course, you wouldn't do a milk experiment and transfer that to blood without doing experiments with real blood. So I'm not saying that you can take a pattern at the scene and reproduce it using something other than blood. You should use blood, but I'm only saying that it's not these are not characteristics of blood uniquely. It's a matter of gravity and physics. So what can you learn from a blood spatter, blood droplet? Basically, you can learn the direction that the blood droplet was traveling at the time that impacted the surface. And if carefully done, you can do that quite accurately. You can also determine within reason the type of weapon or article that had distributed the blood. And you can also, if it's a 90-degree blood droplet, you can make some estimation as to how far the blood droplet fell. Those are the primary considerations, the primary conclusions you can reach. So let's talk about each one of those. If the blood is traveling at a 90-degree angle, perpendicular, straight on, however you want to think of it, towards the target surface, when it impacts, the droplet will be distributed in a circular pattern. So if we have a round blood droplet, we can say that it fell or impacted at a 90-degree angle. The other thing that happens is the further it drops, the larger the blood droplet gets, within reason, of course. After about 4.5 or 5 feet, it doesn't get any bigger. We tested this by dropping blood out the window of the crime lab after carefully making sure no one was underneath the window. We were on the second floor, and we had a driveway directly below our window, and we dropped blood out that window onto the ground below, and it was not substantially larger than blood dropped from 5 or 6 feet. But within that short window, 0 to 5 feet, the blood diameter will increase. To test this, you must get blood. You must get a surface that's the same as the surface which is struck. If it hit a tile floor, then you have to do it on tile. If it hit a paper on the floor, you have to use paper, so forth. And so you then take a pipette and drop blood from measured distances, not just one drop, but several. So you would start at an inch and move out to 3 or 4 inches, out to 5 or 6 inches, out to a foot, out to 18 inches, out to 24 inches, and so forth, with several drops at each distance, and measure the diameter. There is some variation, and you can't be absolutely accurate. But as with other things, you can establish a range. So then you can draw a graph with the diameter on one axis and the distance on the other axis, and then compare your unknown sample to your graph and establish a range. So you wouldn't say, well, this dropped 1.5 inches. You'd say this dropped 0 to 3, or something like that, 4 to 10, some range that gives you some leeway, because there is, as you probably noticed if you have done the bloodstain assignment, that while the overall statement is correct, the devil is in the details, and there are those exceptions where it doesn't enlarge as much as you would anticipate. The next thing is, as it increases in size, it also increases in irregularities to the edges. If you drop blood on a mirror or a glass, the edges of the droplet will be fairly smooth. If you drop them onto cardboard or wood, you will see that as you increase the distance, the edge of the droplet becomes less regular, and eventually you'll see little secondary or satellite drops that are splashed off the main drop and are around the edges. And so that's another thing that helps you determine the distance that it's has fallen. Of course, we're just talking about the acceleration of gravity. So you could do the same if you went to a crime scene and there was vinegar spilled around, you could do the same kind of experiment with vinegar and be as accurate as you are with blood. So if the blood is not traveling 90 degrees, upon impact, inertia will carry the large portion of the blood forward in the direction that the blood is going. So you'll get initially something that looks like a teardrop. I should say that, or a raindrop. I should mention that liquid dropping in air is not in the shape of a teardrop. It's in the shape of a sphere. It only forms a raindrop, or has a point on it when it impacts, and that's because of the forward momentum or forward inertia of the liquid itself. I will now show you some photographs to illustrate that. Here are two blood droplets. The upper one is slightly elongated with a small satellite drop off to the right side. The lower one is even more elongated and has what you might call a tail. We call it a tail, but that's a bad word to use because it doesn't indicate that it's at the back. It's actually at the front. The point of the droplet will show you the direction that it was traveling. So the upper droplet in this illustration was not traveling at as steep an angle as the lower one, and it continues as you change the angle. This is a chart from your book showing various angles starting with 90 degrees or perpendicular and going from 90 to 70, 50, 30, and 20, and on down to 10. You can clearly see the elongation that occurs and the increase in the amount of spatter around the edges of the droplets. This is a pretty reliable indication. If you were to draw a line along the middle of the droplet in the long axis, that will tell you the direction that the droplet was traveling at the point of impact. In this photo, we see many droplets, most of which have tails pointing in the direction that they were traveling. And if you observe it just in general, you see that it forms a fan-like pattern, indicating that there was one point of origin that sprayed out in many directions. If you were to draw lines through several of those droplets, the lines would converge, and you would have a pretty good idea of where the object was that was the origin of the blood droplet. Now, again, we have to be a little bit cautious, and we don't want to make these kinds of determinations based on one droplet. We want to make sure we have a number of them and the number of lines, and the more data we have, the more confident we are of the accuracy of our results. This test will determine the two-dimensional direction, that is the direction in this case on the paper, but in order to determine the third dimension, you need to know the angle at which the blood droplet hit the wall or hit the floor or whatever it hit, and this can be pretty accurately determined using a little mathematical formula. Now, before we do the formula, I want to explain that this formula is based on the formation of an oval and a little trigonometry, which will make it very simple for you to use. But if you have a blood droplet with a long tail, you need to establish where the oval would have stopped had there had it stopped. So I'll show you what I mean. In this droplet, we can see on the right side of the blood spot the formation of a fairly oval shape, but down near the left end it's darker because the blood has somewhat pooled there, so there's a little more of it. But also we have a point, and that interrupts the formation of an oval. So rather than measure the entire length of that droplet, we would measure down to where the oval would stop. So you can kind of continue the direction of the right to left sides of the droplet until they intercept, and then measure that distance. So to determine angle, we use a pretty simple formula as follows. We measure the length of the droplet and the width of the droplet. Then we divide the width by the length, and then we calculate the inverse sine, which on your calculator will look like an sin -1. That means inverse. So in the example given in your book, they have a droplet which is 11 millimeters wide, 22 millimeters long. 11 divided by 22 is 0.5. So then you go to your calculator and you find the inverse sine button, which usually is a secondary function. And all scientific calculators will have the trigonometric sign on them. And like if you have I have an iPhone, and when I go to the calculator on my iPhone, if I turn it sideways, then it turns into a scientific calculator. So you simply push the inverse sine button and enter 0.5, and it will come up with an angle. That angle represents the angle off the wall, not off the perpendicular. So that will then tell you how far off the wall the blood droplet was when it originated. So if you can then take a string and attach it to the droplet, and then string it out on the appropriate angle, then you know that the droplet originated somewhere along that string. This is not as complicated as it sounds, nor is it as accurate as some people would lead you to believe. It doesn't tell you where on the string, it doesn't tell you how far away. The method of determining distance works only for circular drops, not for other angles. So you can't determine how far away based on the size of the drop. But it's a nice way to at least have an idea of where the droplet came from. Sometimes if you examine the crime scene and you can and you know where the event occurred, the droplets that are flung off the weapon in an assault, maybe they're flung off a club or off a knife or off some weapon. Anyway, once in a while you can determine whether the blow was struck from a right-handed person or a left-handed person. A very famous case, which is mentioned in your book, is that of Sam Shepard. Sam Shepard was the doctor in Ohio who was accused of murdering his wife, and that crime was highly publicized. In fact, the movie and the television shows called The Fugitive were sort of based on that crime, although they took many, many liberties in the production. But in any event, Dr. Shepard's wife was beaten to death, and there were droplets on the wall that indicated it was done by a person holding the weapon in their right hand. Dr. Shepard was left-handed, and that was the most famous of the early bloodstain pattern cases. But that's a pretty accurate and well-recognized technique. If you have a situation where there were multiple blows, it's very unusual for the wielder to strike at the same angle every time. So you may have several impacts, and when you draw lines or draw strings through the middle of those, you may get several intersections indicating several drops, several blows. This you can interpret as being a minimum number. It would normally be at least one more than the number of impact sites from the blood, because the first blow would not have much blood. That's the first blow, and so it causes the wound, and then a very short time occurs before blood pools up enough to get on the weapon and thus be flung off. But of course, there could be other answers. There could be a blow that doesn't strike an area that's broken open and bleeds. It maybe hit them in where they have clothing or something. So it's a minimum number, but it's still a good number. And once in a while, if there was movement, maybe the victim takes off and runs or walks away and gets hit again, then you will be able to determine that there was that sort of activity. We had a case in which a man was approached in his home. He was a cocaine dealer, and for some reason several of his customers came to rob him, and when he opened the door, they shot him. He slammed the door and ran to the back door, and they ran around and shot him again. And they chased him around the house and shot him 4 or 5 times more, and we were able to trace his whole route by blood droplets in the house. So that's the sort of thing you can do, depending on if that's important and if the blood drops are appropriately distributed. Another phenomenon occurs as blood is flying through the air. The blood tends to break up into smaller droplets, and the faster the blood is traveling, the smaller the droplets will be. So if you look at a blood spatter pattern, you want to try to determine whether it was low velocity, medium velocity, or high velocity blood spatter. Low velocity, the majority of the droplets will be larger than 4 millimeters in diameter. Now, that doesn't mean you could just take one droplet and extrapolate that. You need a pattern. But in the low velocity, which is blood that's flipped off or dripping, then doesn't have very much speed, and the droplets are larger. If they are medium velocity, which is usually an impact from a blow using some kind of a weapon, a board or a hammer or whatever, then the blood will be traveling a little faster and break up into smaller particles, and most of the droplets will be from 1 to 4 millimeters. The third classification is high speed. High speed blood spatters are the result primarily of 2 different phenomena. One is gunshots, and the other is coughing or sneezing. So if you have a blood spatter in which the majority of the blood droplets are smaller than 1 millimeter, and in particular there are blood drops so small that they can't be measured because they are like a mist coming out of a spray bottle, then that's high speed blood, and most commonly caused by a gunshot, particularly the exit side of the wound. Again, finding one or two small blood spots does not allow you to determine that it was higher, medium, or low, because you get a few that are out of the norm. And so let me show you a couple of examples of gunshot wound sprays. This is a good example of high-speed blood. You can see there are some fairly large droplets on the left side, but on the right side, it's more like a blur or a spray, and that is what you look for before you can determine high-speed blood. This picture shows a woman who has been shot in the head, and if you look at the blood right off to the right of her nose, it appears to be high-speed blood spatter, but a close examination would indicate that that is not from a gunshot wound, but from her coughing. If you get blood in your mouth or in your respiratory tract and you sneeze, blood is propelled out at high speed, and you have to be very careful not to confuse that with a gunshot wound. Sometimes you just don't know, so you say, well, it's either a cough or or a gunshot wound. In this case, we determined that she coughed and remained alive for a few seconds after she was shot, and began to bleed and had blood in her nose and in her mouth, and so we get a coughing pattern. This picture shows a large, severely bleeding area when the victim was standing in the same place for a short time. If you have large wounds, the blood droplets will be very large. As you can see, these are in excess of 10 or 11 millimeters. And this gentleman was standing on his porch after he'd been shot a couple of times and bleeding. Sometimes we get an impression either because the tool is bloody or because they have stepped in a pool of blood. This shows where an individual who had a bloody hand grasped this corner of the door and left the imprints of his 4 fingers. Sometimes they are good enough for fingerprint identification. Oftentimes we need to do things to enhance that impression. Sometimes they can be shoe prints, and if you have done the assignment on blood collection, you will remember the shoe prints in that house had good patterns on them. So the possibility of learning something other than what the blood is there if you can find an image that represents something they've touched or disturbed. It's very important that bloodstain evidence be properly documented, and this usually means photographically. Before you have disturbed the blood, either by testing or by attempting to enhance an image, you need to carefully photograph the stain or stains, and that requires close-up photographs with rulers that measure in millimeters or smaller, and that you are able to determine which drop you're seeing in the picture. So you have to label each drop that you're going to photograph and make sure that the label is incorporated into the photograph when you take it, so that you can then say, well, this is blood drop A, and then you can show a wider picture of the drop showing where A is, and B and C and D and so forth. We will spend some considerable time in the next lecture talking about testing for various body fluids. So in this, we just need to make sure we document it carefully, and if available, you should have a known, well-qualified expert come to the scene, and that will greatly enhance his ability to interpret. Photographs are great, but nothing beats going to the scene.